Yeah, go for it.
Okay, so today we're going to talk about meteorology. So does anyone know what meteorology is, or has anyone ever heard of it before?
The study of weather.
So the study of weather and the study and the science of the atmosphere kind of. So have you guys talked about the atmosphere before in some of your classes?
So, do you guys hear the question?
Our class in in sixth grade, they've talked about the places where clouds are in the atmosphere, but they haven't talked about the actual atmosphere.
Okay, yeah. So that's something we're gonna talk about today too. We're gonna talk about clouds and stuff. So let's transition to talking about the atmosphere. So so the first picture right here shows the different layers of the atmosphere. It's kind of laggy, but it's fine. Okay. Okay, so these are the different layers of the atmosphere. So we have the troposphere, the stratosphere, the mesosphere, the thermosphere, and the exosphere. So have you guys ever talked about any of these layers before?
Yeah.
So, what do you guys know about those layers? You should tell us some fun facts. Tell your classmates. Yes. Hello, can you hear us? I guess just the phone number.
Okay, so let's first talk about the troposphere. So as you can see on this, on the diagram, the troposphere is the one that's closest to our planet, or to the ground, I guess. So the troposphere is the lowest layer of the Earth's atmosphere. Okay, so it's the lowest layer of the Earth's atmosphere, and it contains most of the mass of the atmosphere too. So like someone said before, clouds are in our atmosphere. So most of the types of clouds that you would see if you just looked up would be in the troposphere. So if you look up and see a cloud, that's most likely you're looking at the troposphere. And then also almost all of our weather occurs here too. So if we have like cloudy weather, then obviously it'll be from the troposphere, because most of the clouds are formed in the troposphere or found in the troposphere. And then like rain and snow and just weather like that. So a lot of the weather occurs here too. And something important about the troposphere is that as you go higher up in the troposphere, the air gets colder. So like for example, if you're climbing a mountain, as you get higher and higher on that mountain, the air would get colder and colder, and also the air would get thinner too. And then also it's also made up of 78% nitrogen, 21% oxygen, 1% other gases. So Neha, did you have a question?
Yeah, I was just wondering what you did last week. Apparently I didn't join. I have no idea that I didn't join. What did you do last week?
Well, last week you kind of missed the lesson on what was that again? Space and black holes and Hawking radiation and all kinds of fun stuff. And yeah, you kind of missed that. But hey, on the bright side, it's on the Super Portal if you want to watch.
Okay, yeah.
So
can you put the link again for the Super Portal?
Sure, I'll put a link there. But yeah, today is the lesson that you people in this class badly requested, which was the weather. So
that was me.
Yes, you. Actually, no, the other class also people bugged us for the
But
last.
mainly me.
Yep, it's all you. So enjoy. Yep.
Okay, so
I'll post it though.
Yeah. Okay, so the next layer is the stratosphere. So the top of the stratosphere is about 10 kilometers above the ground, and the top of this layer is at 50 kilometers. So basically the stratosphere, so if the bottom of the stratosphere is at 10 kilometers and the top of it is at 50 kilometers, how large would the stratosphere be? Wait, I didn't hear you.
Is it 40 kilometers?
Yeah, 40 kilometers. So the stratosphere is 40 kilometers. And also the stratosphere is where jets like to fly, and like airplanes and aircrafts and all that. And weather also occurs here. And also as you go higher up the stratosphere, the air gets hotter. So it's like the inverse of the troposphere. When you went higher up in the troposphere, the air got colder, but in the stratosphere, as you go higher up, the air gets hotter. Okay, and another very important part of the stratosphere is the ozone layer. Has anyone ever heard of the ozone layer before? And what do you know about it?
I
I
think
heard
I've heard
it in a
about it.
joke, but like I think algae created it, and it's protection from the sun.
Yeah, it's like protection from harmful rays from the sun and like UV light and everything. And so the ozone layer helps us because it shields us from those harmful rays, and also it can turn the UV light into heat that warms up the planet too. And then the stratosphere also contains 20% of atmosphere's mass. So like we said, the stratosphere is above the troposphere. And so if there are a lot of clouds in the troposphere, we would most likely be higher than the clouds when we're in the stratosphere. So have you ever guys, when you guys were on a plane, have you ever like looked out the window and saw the tops of the clouds? And it was like you were flying above the clouds?
Yes.
Yeah, so that can be explained because you guys were actually in the stratosphere, which is where all the airplanes like to fly. So when you guys are in the stratosphere, you're above a lot of clouds. So that's why you can see the tops of the clouds when you look out of an airplane window. Okay.
Amrita, can I add something on the ozone, by the way?
Yeah.
So one thing we probably heard of it in classes before, guys, but do you guys know the concept of breaking the ozone layer? You guys have probably heard it before, right?
Yeah.
What do you guys think? How do we break the ozone layer? What do you guys think? How do we do that? What do you know about breaking the ozone?
I guess you need like a lot of energy.
True, but
We're releasing gases that can break it, I guess.
yeah. So the interesting thing about the ozone layer is that the ozone layer is special because what happens is that when the ozone, basically, when you hear ozone, the molecule that's ozone itself is something called O3. And if you think about O3, it's just oxygen. Instead of O2, it's got three atoms of oxygen, and that is one molecule of ozone, basically. So if your ozone itself is naturally created when UV radiation hits oxygen molecules and then breaks them into single oxygen atoms, and then by chance they basically form into O3, which is just three oxygen atoms attached together. And the way we break ozone is basically, Shriyansh, do you have a question?
I thought algae created ozone.
Algae? Well,
Yeah, I thought they created the ozone layer.
there's multiple ways to create the ozone layer, but most of the ozone layer is created by UV radiation hitting oxygen and gas molecules. It's there's a lot of ways that the ozone was created, and if you explore the creation of the universe, you can definitely get into all the different ways. But one of the cool ways is because UV radiation, ultraviolet radiation, kind of breaks the natural structure of oxygen gas, and then they bond together to make it to multiple 3 oxygen atoms together. But let me add an important thing. So have you guys heard of the thing called chlorofluorocarbons before? CFCs? You guys have probably heard of it once. Any of you guys? No? So CFCs are these things that have multiple atoms in it, carbon, fluorine, and multiple chlorine in it. And these things are really harmful because those are the things that are in our hairspray, our aerosol containers, our AC refrigerant. So that's how ACs stay cold. Basically, we use these special gases, and when you release these into the atmosphere, UV radiation breaks the chlorine off of this chlorofluorocarbon, and that free chlorine is gonna pull oxygen from ozone. Actually, Amrita, I will you keep going. I will show them a picture. I will show you guys a picture a little later on how this happens. But it's a really interesting process, actually. You guys should know about it. So Amrita, you can keep going, but I'll add to that in a bit.
Okay, so next we're going to talk about the mesosphere. So we talked about how the stratosphere ends at 50 kilometers. So the mesosphere picks right back up at 50 kilometers, and it exists until 85 kilometers. So that's about 35 kilometers. And the temperature decreases as the height increases. So that's just like the troposphere. So when we said that it got colder as the height got higher, that's the same thing that happens in the mesosphere too. And then the mesosphere is also the coldest atmospheric layer. So it has a lot of CO2 particles in it. So that helps keep the layer cold. And also, since it is really cold, it can also make these clouds called noctilucent clouds. And basically when it forms these, it's like it freezes. So in the mesosphere, there's a very small amount of water vapor. So it can freeze this water vapor into little ice cubes and make clouds filled with these little ice cubes. And that's what makes up noctilucent clouds. And then also the mesosphere also plays a role in blocking out harmful cosmic rays. So just like the ozone layer, this also helps protect the Earth from harmful rays from space. And you might have heard of how the atmosphere. Oh, is someone talking?
No, but I did hear some other noise. But yeah, you can keep going.
Okay. Okay, so it blocks out harmful cosmic rays from space. And also you guys might have heard that our Earth has the ability to burn up stuff from space like meteors or asteroids or other debris. So the mesosphere is where these meteors and other debris burn up a lot. So that's also a very important reason why the mesosphere is an important part of our atmosphere. And right here is a picture of those noctilucent clouds. So they're kind of blue, and they're all made up of tiny ice cubes. So if you guys ever see these types of clouds, remember that they're formed in the mesosphere. So basically you're looking at the mesosphere. Okay.
Any questions actually before we go on? Wait, Shriyans, do you still have that question? My bad.
I forgot to lower my hand.
Oh, okay. All right. Yeah, you can keep going.
I have a question.
Yes?
Oh, you can hear me. Sorry, I joined from a different desktop. So I was wondering if we're going to learn about like weather patterns and like tornadoes and storms and lightning, like that.
Yeah, we're gonna cover a little bit of that, but I mean, the thing about weather patterns is that, well, yeah, I guess we can talk about it, but the thing about weather patterns is it's largely dependent on where and how where you look at in terms of like these pretty basic information. If to like think of like this kind of climate, which is I think this kind of place is gonna have this kind of weather pattern. It's what I would call like rather basic in the sense we can talk about it, but we're trying to at least show you guys maybe a couple of new things that you may not have known of. So yeah, we'll talk about it a little bit at the end, I guess. And yeah, let's also I really want to talk to you guys about how we actually like all this stuff about ozone because it's super interesting. Yep. All right. Okay, let's keep going.
Thank you for answering my question.
Wait, were you trying to speak the whole time and we couldn't hear you or something?
No. I muted myself on purpose because I had background.
Okay. All right. Okay. All right. Nice. Thanks. See ya. Yeah. Okay. Keep going, Ruta. Please.
Okay, so now we're going to talk about the thermosphere. So the thermosphere is from 90 kilometers to 1,000 kilometers. And okay, so and then in this, the temperature increases as the height increases. So that's like the stratosphere. Remember, the stratosphere, in the stratosphere, the temperature gets hotter as you go up the stratosphere. So the thermosphere is really hot, and that's because it can absorb the sun's radiation. So if you look at this bottom bullet point right here. So when the sun is really active, the thermosphere expands or puffs up as it gets hotter. So the temperatures can reach really, really high, like 1,727 degrees Celsius. And because it's absorbing all this heat, the thermosphere allows our temperature on Earth to be more moderate and not as hot as it would be if we didn't have a thermosphere, because all that heat would go on Earth. So that's why the thermosphere is really, really hot. And this is also where a lot of satellites go also. So that's something important to know. And also, since it's really hot, there's a lot of movement with a lot of particles, and it creates light shows like the aurora borealis. So this is a picture of the aurora borealis right here to the left. So it's like one of those green wispy things in the sky.
Drew, do you have a question?
Yeah, about the thermosphere, I have a question.
Yeah.
So doesn't thermo mean sun?
Thermo means since thermo means heat. So I mean you can call it that, but thermo the word thermos itself, yeah, it means heat. Shivan, here's the Latin.
Yeah, the thermo is derived from the Latin word for heat or energy.
Yeah, and Neha, do you have a question?
Yes, I do. So I was wondering where you can find the aurora borealis. Is it like anywhere or like a specific?
So the aurora borealis is found really near the Arctic. So near the North and South Poles. So like if you live in like the upper parts like Sweden or Norway, like really, really high in Europe, you could see it, but mostly you'd have to travel like Iceland, Greenland, or maybe even to the Arctic itself in order to see the aurora borealis.
Yeah, so northernmost latitudes are usually where you will see it. So if you like take a globe and then look at like Greenland, Alaska, Yukon, and various places in Russia, you'll probably see it. Yep. Yep. Okay. All right. Any questions? Do you have another question, Neha? Or? Okay. All right. You can keep going on Ruth, I guess.
Okay. So yeah. So that was the thermosphere. And the Next is the exosphere. Oh my gosh, sorry. Sorry.
That always felt like a jump scare for me for a second there.
Yeah. Let me just mute myself.
Hello? Wait. Shavika, Amrita, what happened?
I think Amrita muted herself to ask her dog to be quiet.
Okay.
Yeah. Okay, so we'll just go over the exosphere really quickly until Amrita comes back. Okay, so the exosphere, right? It's the last layer on the sphere, the layers we're talking about. So it's basically the edge of the thermosphere in space. It's just like that last layer. So it's really thin. It's made up of mostly helium and hydrogen. So we wouldn't really be able to breathe there. We wouldn't need our spacesuit or something like that. It's the farthest point on Earth still affected by Earth's gravity. That's why we consider it a part of Earth's atmosphere, even though it's so on the edge. It's 10,000 kilometers. Is that 10,000?
Yeah.
Yeah. 10,000 kilometers.
Yeah.
10,000 kilometers thick. And it just goes off into interplanet. It just becomes space at some point. Like there's just no like line, right? And it's the first part of our atmosphere that our sun's rays go through. So you can see like as we go down, the sun's rays get less and less harmful because we have so many parts of the atmosphere trying to lessen the effects of those UV rays. And it's also the first layer that you can like meteors and asteroids slowly start to break apart so that once they get to the Earth, they don't do any real damage. And so that's about it. Do you have anything to add?
The exosphere, the prefix exo is derived from the Latin word meaning outer. So the outermost sphere is exo, so exosphere.
Yeah, exo means usually like out.
Like outside, like exoskeletons on the outside. Exosphere
or like
is the outermost
exothermic
layer.
when you're like releasing heat.
Yep.
Okay. Now we're gonna do weather instruments.
So, actually, before that,
Okay.
what do you guys know about weather instruments? What are we trying to measure? What is weather consistent of? Just some random questions, actually. Tell us.
Maybe like the seasons, maybe.
Okay, that's a start.
Like when you look outside on a regular day, what do you feel? You feel heat or you feel humidity, things like that.
Weather is like the daily change of how it feels like outside, I guess.
Yep.
Yeah, that's good. Okay, so scientists and weather people air pressure there is, how humid it is. Humidity is the stuff that makes your hair all frizzy and your skin sticky, right? A lot, especially in the South. If you live down here, it gets really gross. And so there's different things that scientists use to measure different parts of the weather. So there's the basic things like thermometers that measure temperature. And if you've ever seen a thermometer, there's a little liquid at the bottom, usually alcohol or mercury. And based on how hot or cold it is, the liquid at the bottom expands and contracts, and it goes up the little tube, right? And you can see how hot or cold it is. So that's what a thermometer does. They do that outside for the temperature as well. And okay, and then next we'll do wind vane. So you've probably seen on like tops of houses or barns or something like that. They have these little decoration looking things with like a chicken on top usually or something. They usually look like they're decoration, but they're actually like they show which way the wind is going. So it'll turn based on what direction the wind is going, right? So you can see the wind, if it's pointing west, you can see that the wind is blowing westward or eastward, north or south. And so it's just like a really simple way. A lot of these instruments you'll see are pretty simple. They're pretty simple, but they measure things that scientists need to predict weather patterns, things like that. And then next we have a rain gauge. And this one's pretty simple too. Basically, it's like a fancy cup, like a tube, right? And it has little measurements on it in millimeters. And so it catches water. So it just records like every day, they'll just check how much water is in it. And it records water over time so you can see how much precipitation is falling over time. And they make lists. They compile it all together and they'll say, in the month of September, this much water was there on average. In October, this much. And it can be any type of precipitation, right? It can be snow too, because snow can melt into ice or water. Sorry. And then next we have an anemometer. So this one,
should I speak in Sharvika? You're kind of getting out of clearness.
Yeah.
Okay, so an anemometer is like this weird thing, kind of, that's like these three little cups that are on a rotating spindle. And what this does is that this allows us, these cups catch flowing wind, as you can see, right? Oh, wait, I'm not controlling the whiteboard, but whoever is controlling the whiteboard, are we zoomed in on the right thing? Actually, you guys probably don't see the whiteboard. Okay, so an anemometer. What happened?
Wait, can
You can start sharing again if you want to.
Wait, can you hear me?
Yeah, you guys, I think, are having some kind of internet glitchery today, but it's okay. Neha, do you have a question while we're at it?
Yeah, isn't there, I don't know what it's called, but I kind of have to draw it to actually be able to explain it, but it's another weather tool.
Do you know what it's trying to measure, this weather instrument?
I think it's trying to measure like wind related. I think it's wait a second. I think it has like a stick and then it has a sock like thingy and there's little designs in the sock. And then like whichever direction the wind blows, it flies that way.
I think you're talking about a windsock.
Yeah, the wind.
Yeah, that thing.
A windsock is a rudimentary instrument that allows us to define the direction of the weather, the wind that is blowing, and also gives us a visual interpretation of how much wind is actually flowing. So the thing is, if you looked at a wind vane, you're only going to see the direction of the wind that is going. However, a windsock provides a visual for us to see how strong the wind is, while also giving us an idea of what direction it's flowing in. So even though it's not completely accurate, you can't like really attach sensors to windsocks to like find the parameters of weather. This, if you put this like near like, I don't know, a runway, if a pilot was flying his plane, he can take a look down, he can take a look from his window and see, oh, okay, the wind is blowing that way and it's blowing really strong. Maybe I should be a little careful and not crash the plane. So that's kind of the point of a windsock. Does that make sense?
Yeah, it's like kind of the point which direction the wind's going.
Yeah.
That's something that I noticed. You said that the pilot should go careful and try not to crash the plane, but shouldn't a pilot always do that?
Maybe we shouldn't ask logic questions. Yes, pilots shouldn't be crashing planes. Yes, good answer. Yeah, so that kind of gives us an idea. Ruth, are you there? Do you want to talk about the next thing, I guess? Did we go over some of the other ones?
Wait, did Sharvika finish all her instruments?
I have no idea, but let's just keep going. So actually, yeah, after anemometer, we talked about rain gauge, thermometer, barometer. We should also talk, okay, Campbell-Stokes. Can you do it or should I do it?
You can do it if you want.
Okay. So the Campbell-Stokes recorder is basically this special device which has this special kind of paper that is inside it. And what it does is that it absorbs the rays from the sun, so photons from the sun, and this paper reacts to the energy that flowed right into the paper. And depending on how the paper reacts to it, scientists can use a computer, and what the computer will analyze how sunny it was. So what's like the UV radiation, like, because the heat and radiation is not correlated always, because when you walk outside in the afternoon, even if it is the same temperature as you walk outside and it's the evening, the amount of sunlight that is still hitting will be a little different. And that's because that's the difference between heat and radiation. So this Campbell-Stokes recorder can see how much UV radiation or ultraviolet rays that are coming from the sun. And this card records it, and scientists can use a computer to analyze how much it is. So how basically burnt this piece of paper inside this fancy little thing is what they do. Do you want, should I go on to the next one? Any questions on that? So do you guys understand the difference between heat and radiation? They're two different things. Heat and sunlight are never correlated. Well, they are correlated, but they can be quite different, actually. Does that make sense?
Yes.
Do you want to go to the next one, Amrita, or I can go?
Like the next topic or the next instrument?
No, the hydrometer. Hydrometer. I can never say that right. Ian, do you have a question, by the way?
Yeah, is the paper inside the glass sphere, or is it outside?
So it's right below the glass sphere. So the glass sphere allows sunlight to be absorbed into a point and be focused onto the paper. Does that make sense? So it's actually...
So is the card the paper?
Yeah, the card. The card is the fancy paper. It's like treated paper, basically, with some chemical on it.
So after it is pointed, it's used on a computer to see the radiation.
Yep, and if and some of these older versions of these Campbell-Stokes recorders, the older versions, just by looking at how different the paper looks like, scientists were able to see, okay, it's this sunny. Like they could look at the color and identify it, basically. Does that make sense?
Before they had computers.
Yeah, before computers were very mainstream in this kind of application. So
Okay.
yeah, so let's go on to the next thing, I guess, which is the wet and dry bulb hydrometer. So hydrometer, it sounds like hydro, and when we think of hydro, we think
Oh, we need a hydrometer, but it says a hygrometer.
yeah, I don't know why.
Was that like a typo or something?
It probably is a typo, but it's, yeah. So hydrometers basically measure humidity in the atmosphere, and they do this through this wet and dry bulb kind of technology. And I wish I could like tell you more about it, but it's pretty simple. It just measures humidity, and like we shouldn't really, there's not much to bother about how it really does it. But yeah, I think we covered kind of all the different devices, these weather instruments that scientists use. But I should actually go on and tell you one thing about these things. All of these are measuring for what? What are they measuring for collectively, all of these things? What are they measuring for collectively, according to you guys? What are they measuring for?
Like the type of weather, like will it be windy, sunny, or like rainy?
Yes, and what do we call these things that can make up weather?
Is it climate?
Okay, so actually we should establish that difference too. So what I was actually looking for are either parameters or variables. All of these are variables that allows us to see what the weather is like. All of these are various variables which make up our weather, right? So let me explain to you one small thing. Back in the old days, scientists would use these variables, and what they would do is by using these variables and then looking at records that they formed over many years of recording on paper, they would look at these old records and look at the variables and try to find older records that were very similar to it. And based on that, they would make predictions. They'd be like, okay, so 3 years ago, it was like this at this day. Okay, so therefore, tomorrow's weather is going to be like the next day's weather that from 3 years ago. So scientists did that a long time ago. But today, scientists basically collect all these different measurements, and what they do these days is that they use computers, and they input all these variables into computers with a ton of data inside it, and this is more data. And the computer basically uses this algorithm called a sliding window algorithm. And basically, sliding window is this algorithm that scientists developed over many years. And what they do is they look at weather comparisons from 3 years ago. So if I was looking at the weather today outside, it's a very sunny and warm day. I would compare today's weather to what it was like and try to find a similar day like today in the last 3 years. And by looking at the last 3 years data, scientists have found that if you look at this amount of time between the present and the past, you're able to predict the weather with about 92% accuracy, which is actually incredible when you think about it. So we have reached a point in modern technology where we are able to predict next day's and the coming days' weather by 92% accuracy. And that's down to the degrees. So it's actually incredible. And I hope that gives you a little sense for how advanced your weather prediction skills have become using technology. Does that make sense? Any questions? Anything? No questions? Okay, let's keep going then. Amrita, what do we cover next?
Clouds.
Well, you can get to it, I guess.
Okay. Okay, so basically, for the clouds, I'm just gonna go over like the 4 like basic types, but like all of these types can be like kind of combined to create new types, which I'll show you guys after. So the first one is cumulus. So cumulus is kind of like a cloud that has a flat base. So like right here. Wait, can you guys see my mouse?
Actually, if you okay, I can annotate as you speak. All right, go for it.
Okay, so it has flat bases on the bottoms of the clouds, and then on the top, it's like really puffy and like fluffy and kind of like something you would see in like a cotton candy or something like that. And so cumulo is actually, I'm pretty sure it's a Latin word, and it means like heap or pile. So you can see that cloud on the flat base, it's like piling on it's like a pile of fluffiness and a pile of cloud, cotton and stuff. So whenever you see a shape like that, know that it's kind of like a cumulus cloud. And so this kind of cloud indicates fair weather, but if they keep piling up on each other, they can pile up so much that they can create rain showers and precipitation. Okay, so the next part is, the next one is cirrus. So cirrus clouds are more like thin, wispy strands. So cirrus is also kind of a Latin word that means like curling lock of hair, or like thin locks of hair. So as you can see in the picture, it's kind of like strands of hair that have been like curled upwards almost. So it's like wispy and thin. And it looks like how it would look like if you took a cotton ball and just kind of like ripped it apart until it was like thin and wispy. And cirrus clouds are usually composed of ice, and they're usually white. And they predict fair and pleasant weather. And then, like I said, you can combine these clouds almost. So cirrocumulus is when these cirrus clouds are like piled up on each other, and they form in the winter, and so they would predict cold weather. Does anyone have any questions on those two types of clouds?
Speaking of clouds, how many of you guys actually like cotton candy to begin with?
Me.
Me.
You guys like cotton candy? I could never stand cotton candy, for God's sake. I don't know about, what about you, Shivan? Did you like cotton candy? And the Shivans are gone. It seems that's kind of sad. What
I
about
have
you?
a question.
Yes.
So is cirrocumulus like cirrus and cumulus combined, or is it just cirrus stacked on top of each other?
And that's a question for Amruta, actually, because she's the cloud expert for today. Amruta, do you know?
It's kind of like both. So for cumulus, it's like they're piling up on each other, right? So like I said, cumulus means heaps or piles. So if it's cirrocumulus, it's like a bunch of cirrus clouds piled up on each other, and they're piling up, and so they, wait, can you go like to the next two? Next, stratus and nimbus. Yeah. So the next two parts we're going to go over are
Yes.
are stratus clouds. So stratus clouds are really low level clouds. So they're like horizontal layering with a uniform base, and they usually look gray. And also since they're low level clouds, they can also be capable of ground contact if they get low enough. And they're accompanied by little to no rainfall, but if they're piled up on each other, they can actually produce a slight drizzle. And also it kind of looks like fog too. So since fog is really low on the ground, it's kind of like these stratus clouds because they're very low level grounds.
Fun fact, you can usually, if you have a somewhat decent drone, you can usually fly past a stratus cloud if your drone's somewhat decent. I've done it before, and like it's so cool seeing video from like above the cloud. It's really interesting. You guys should try it sometimes, or get a drone and try it. Very fun. Oh, okay.
On nimbus, does it say, is it supposed to say thick enough or thin enough?
Yes, thick enough, sorry.
I sure do. I go around with them. Yeah.
So
Small
nimbus clouds are dark and they're gray. So as you can see in the picture, they're really dark and gray, and they're kind of scary looking. So they're thick enough to block out the sun. So they're really thick, and they can indicate persistent rain or a lot of precipitation. So there's kind of a trend among all these clouds. If they pile up on each other and become thick, then they usually predict rainfall or precipitation of some kind. So that's just something to notice. And also, have you guys ever heard of cumulonimbus clouds?
Probably heard of it.
Yes.
Yeah.
Yeah, so cumulonimbus is also another example of combining both of those. So cumulonimbus are like kind of nimbus clouds, but they're like really piled on in like heaps of nimbus clouds. And so this picture that Ivan's showing on his screen, they're like more variations of all these different clouds. So, so for example, nimbostratus. So stratus clouds are low-lying, right? And nimbus clouds are like dark and gray. So that's why these nimbostratus clouds are nimbus clouds, except low-lying and a little more like wispier, kind of.
Yep.
And then, yeah, and over here below cumulonimbus, you can see the noctilucent clouds that we talked about before. And does anyone remember which layer of the atmosphere noctilucent clouds were a part of?
Anyone? Take a guess. You only have like 4 layers. You can guess.
I think it was like the third one, maybe.
That's close. It was the one right below it, so the mesosphere. The mesosphere can form new noctilucent clouds.
Yeah, that's
Okay.
No, he did get it right? Yeah. Didn't he? Yep.
Well,
I mean,
I had it under the.
I mean, if you don't count the ozone, if you count the ozone as a layer, I guess, but like, you know, it is. So, yeah, it is the 3rd layer. Cool. What's next, Amrita? What else did you want to talk about? Oh wait, yeah.
That right there.
Okay.
I must say, annotating is a hard job.
Wait, what?
Did you realize I was annotating the whole time?
Yes, I did realize. Can we not?
Yeah, sure.
It's not hard when you're Audubon and you buy a tablet off of Amazon that makes it like you're writing on a sheet of
Mouses
paper.
make
except it
life
shows up on the
harder.
screen.
You should never annotate with a mouse, and you should especially never annotate with one of these devices if you've never used one of these. These are called trackballs. You should never annotate.
Are those from like the 1900s?
Wow, that's a little okay. So it's actually a technology from more like the 90s, and yeah, it's super
Old. It's still old.
You guys should try.
Mouses are the new deal.
You guys should try it. It's super fun. But yeah, thunder and
In
lightning.
your dreams.
Okay.
Well, there's one last picture in the cloud part that I wanted to go over.
Okay. Which one was it? The contrast?
Sure. Yeah. So wait, yeah. So this picture just basically the blue one, the one right next to it.
Oh, okay.
Yeah. So this picture basically shows like the different types of clouds that are lower and or higher in the atmosphere. So so cirrus clouds are more higher, because remember they're wispy and they're more higher, and cirrocumulus and cirrostratus. So those are like combination clouds, so they're high. And then mid you have like nimbostratus, which we also saw a picture of, and altostratus and altocumulus. And then low we have the stratus, which are low-lying clouds, and then stratocumulus, cumulus, and cumulonimbus. So yeah, so they have.
Yeah, the small question though. What take a guess, guys. What clouds do you think gives us the most turbulence? Take a guess, guys. What clouds do you think gives us the most turbulence of the clouds that you see here? Take a guess. Like when you're flying on a plane and it's like
I think it's cumulonimbus, maybe.
Yes.
Correct. So most of the time, turbulence is a thing where the plane is being rocked back and forth in the air, even though it's a huge huge metal bird. It is rocked back and forth by the wind and by the heavy clouds in the air. Most of the time, you feel turbulence when you are descending or ascending into the air, because once you reach what we call cruising altitude, you're pretty high, and most of the time, the only clouds you will find in cruising altitude, which is around 20 to 30,000 feet, is cirrus and cirrostratus at the most. But when you're descending to the midpoint or the low point, then you start, if you get into these clouds, this is usually when you're going to find a lot of turbulence. But yeah, Just a fun question. So is thunder and lightning next, Amrutha?
Yes. Do you want to take that one?
Sure.
I can take it if you need to.
Yeah, go for it, Shannon.
Okay, so thunder and lightning. This is the fun stuff.
Ooh.
Even though you don't want to be struck by one, that
How
would be
about
bad.
I take this?
Okay.
Okay, class, chop, chop, chop. You need to turn in your assignments in 2 seconds. Okay.
We're in
so
summer break.
we're
We're now
talking
being
about-
ousted. No one likes to turn in assignments.
Well, too bad. You still have class.
Yeah.
Anyways, where was I? Okay, thunder and lightning. How
Oh,
are
yes.
they combined? Like, how are they related? You could call them cousins in a way because thunder is the sound that lightning makes.
Yeah, so it's more
And-
like a cause and effect, right? So when you get lightning, then it creates a thunder. But in order to really even understand this, we need to understand lightning. This is the root cause of thunder, right? So lightning is
Lightning
actually very
is
simple. Have you guys
electricity.
ever, touched a doorknob and you felt like a small shock?
Yeah.
Yeah. So that's called static electricity. So what's happened is basically you've rubbed against a surface which has a lot of negative charge. And so now your fingers are slightly negatively charged. And the surface of many metals is slightly positively charged. So what happens then is that the electrons that make up the electric charge on your fingertips jump from your hand to the doorknob. And that jump is called electricity, because electricity, remember, it's just a flow of electrons. And so these are just jumping from your hands to the positively charged doorknob. And that's static electricity. All lightning is a bigger version of this. So in lightning, you have a much larger scale, but essentially the same principle. The ground is slightly positively charged, and the clouds have a very slight negative charge. So what's happening is once the clouds build up a negative charge, these electrons are like, no, I want to go be with the positive charges in the ground. So then all these electrons jump out of the cloud and basically go to the ground in what is known as lightning. Okay, so it's just a bunch of electrons jumping from cloud to ground. Of course, you can also have intercloud lightning, which is basically lightning inside the cloud itself. So if you have like a bunch of really big clouds, like cumulonimbus, those are actually pretty large clouds, right? So you can build up areas of positive charge, negative charge within one cloud itself or multiple clouds. And instead of the electrons that make up the electric charge going from the cloud to the ground, it can just go from the negatively charged area of the cloud to the positively charged area of the cloud. So it's all lightning is, it's just a movement of electrons from one place to another. Big scale electricity. Okay. And so when this happens, right, it's going to create a lot of heat. So it can reach temperatures of upwards around 50,000 degrees Fahrenheit, which is actually hotter than the surface of the sun. So when this happens, it's a very rapid thing. So it's basically the air directly around the lightning basically becomes superheated, and then it expands very, very quickly. And so basically that heat travels very quickly outwards, and these particles are very quickly expanding, creating what we know as thunder. So it's like a sonic boom coming away from the lightning because it superheated this air and this heat is traveling by.
May I speak now?
Yes,
I am the
you may
teacher.
speak.
I am the teacher. Anyways, so normally say it's storming and you look out your window. It's not a good idea to look at lightning, but you see the lightning first. You see the light first because light travels faster than sound. And so you hear the thunder later. And many people say that if you count the seconds between the light and the sound, you can detect how many miles away the storm is from your house.
I think it's like 1 mile a second or something.
I don't think that's true, though. It never works.
Let's search it up on Google.
I thought you had to find the difference between like the booms.
Yeah, but yeah. So actually, before we, I guess we can talk about lightning a little bit in a second. I think we need to establish one thing that we need to be aware of. You guys, what is the difference between lightning, or not lightning, climate and weather. What do you guys know about?
Me.
Sure, go for it.
Climate is the
Okay,
temperature.
climate and weather are totally
Okay,
different.
one at a time.
Me.
You.
Okay, thank you. So climate is like weather over a long period of time, whereas weather is how it is in a short period of time. So like if it's sunny today, then that's weather. If it's going to be sunny for the rest of the month or the year or the season, then that would be climate because it's over a longer period of time.
Yeah, so you basically hit the point. Drew, do you want to add anything to that?
No.
I mean, so yeah, climate is basically, that is all there is to climate. Climate is the type of weather that a geographic region faces over an extended period of time. And weather is the short, like a snapshot of the region's weather over a short period of time. So actually, I would associate climate with multiple, with like region. Climate is something that you associate regionally and over an extended period of time. So something like years. Weather could only be a couple of months, you know? Weather, seasons, you know? Ian, do you have anything to say? Any questions?
Can I add something?
Sure.
Like in a tropical rainforest, it's usually hot, but in the desert, it's usually hot. But if it rains one day, that's like the weather. But like you know that the climate of a desert is usually hot because deserts don't get that much rain. So one day if it rains, that's like the weather of that day.
Yep. Indeed. And you hit the nail on the head, basically. Any other questions before we move on to our like one other segment, I guess? Any questions? Okay. Amrita, did you have anything to add or can I move on to the other thing? All right. Okay, we'll move on to that bit. So I wanted to show you guys a little bit about ozone, right? So as we see, ozone is basically not 3 eyeballs, it's 3 atoms of oxygen. And this ozone, that is what we call it. So whenever you see O3, it's ozone. And what happens is that usually we create ozone through this process where we have oxygen gas. And what happens is that...
Wait, 1 second. Can you scroll back down again?
Okay.
To that. Yeah, that. How do you get your lines so straight and perfect and circly and roundy?
I don't know. That is because I was doing it on the whiteboard. It auto does that. Wait, Shivan, you keep going. I'll be back in a second, Shivan.
Okay, so as I don't want to talk about ozone, right?
My best line.
Yeah, the best line, right?
Terrible.
So as he was saying, right? Ozone is basically 3 oxygen atoms that have been bonded together. So the gas we breathe in is just O2, but ozone is O3 because it has 3, not 2 atoms. So normally in the ozone layer, right, how ozone protects us is it absorbs this UV radiation. And when it absorbs this UV radiation basically breaks off one molecule off this ozone. And when it does this, it creates a separate oxygen atom, and then it leaves behind an O2 molecule, which we can breathe in. So ozone is a very useful molecule, serves a double purpose, makes some air for us, and absorbs UV radiation that can hurt our skin and cause cancer.
And the one thing is, the ozone is constantly regenerating. However, it is a slow process, and if we beat the speed of the recreation by the speed of us breaking it down, we're not going to have enough ozone. And if we don't have enough ozone, bad things can happen. Higher amounts of UV rays can go down to the earth, and it can be absorbed by people like us. And if it's absorbed into the skin, you are at a higher chance of getting stuff like cancer or other things. Ozone protects us from, it absorbs a lot of the heat for us. And ozone does a lot of things. I implore you guys to do more research and find other things. But I should probably show you how CFCs break our ozone. So what do we know about CFCs? It's a fancy long word, chlorofluorocarbons. Chloro, which means chlorine, fluoro, which means fluorine, and carbon, oh, what on earth? Carbon, which means carbon. So chlorofluorocarbons are these inert gases that are usually found inside a lot of products that we use around. So hairspray, anything that has to do with aerosol cans has chlorofluorocarbons inside it.
Although, just keep in mind that while they were in a lot of like aerosol products back in the 1980s, 90s, CFCs have actually been banned in a lot of aerosol products nowadays. There's very, very strict regulation on it. And so nowadays, there's actually very, very few products that are allowed to have CFCs used within them, like refrigerators.
And well, actually, even refrigerators, they're coming up with eco-friendly versions where it doesn't destroy our ozone layer. And basically, refrigerators have this special liquid inside them, which heats and evaporates and can cool down back to a liquid. And that's how refrigerators can make things cold and all that. We don't need to explore that today. But this is called refrigerant, and usually that is a type of chlorofluorocarbon, and it is in a. Let me show you the structure of chlorofluorocarbons so I can try to explain it to you. So most CFCs kind of look like this. You have a big carbon atom with multiple chlorines attached on the bottom, which share its electrons with the carbon atom. And okay, can we not do annotation so much? Yeah. So it has this multiple chlorines attached on the bottom, and it has this fluorine on the top, which balances the carbon's electrons. And these are inert, which means nothing's going to happen. They're very stable molecules. However, when you very irresponsibly spray a lot of it to the atmosphere, it floats up because it's a little lighter than oxygen and our atmosphere's layers. And as it floats up, it is going to meet up in the various layers, so the stratosphere. So as it meets in the stratosphere, you're going to see a lot of UV radiation. And this UV radiation basically hits the electrons that hold chlorine and carbon together, and it separates that chlorine. And if you allow that chlorine to float around in the atmosphere, what it's going to do is that it's going to go attach onto ozone, which is O3, and it's going to attach onto ozone and then steal one oxygen from ozone, making it O2. And as we know, O2 can't really help us protect us from the it isn't as useful as ozone, basically. And this is how we break ozone, by releasing CFCs. So CFCs are very inert, stable gases, but as soon as you hit them with UV radiation, it has the power to release chlorine, and that's going to break our ozone, and that's going to then cause us a lot of trouble. So in the early 80s, 90s, even the 60s and 70s, no scientists didn't really care about ozones, didn't really care about CFCs. They thought, oh, it's a stable gas, nothing's going to happen. But scientists became a little wiser over the years, and then they discovered, hey, this is how we're destroying our ozone layer. Maybe we should do something about it. So that's why they started banning these CFCs from usage. So a little lesson on
yes. So these CFC molecules are very, very destructive.
Yeah.
Because once that chlorine takes away that oxygen from the ozone and it forms a ClO, UV radiation, once it hits that molecule again, it'll release the chlorine from that oxygen molecule, and that chlorine atom will go then break apart more ozone molecules. So just one single chlorofluorocarbon molecule has the potential to destroy a lot of ozone. If it's like a 1-to-1 ratio, one chlorofluorocarbon breaks one ozone, we wouldn't have such strict regulation, but that's not the case. One chlorofluorocarbon can break apart many, many different ozone molecules, which is why it's such a problem.
So yeah, so this little one chlorine, very destructive, very little dangerous little guy. You shouldn't be letting it into the atmosphere. And that's why we do a lot of stuff to prevent this. And it takes a lot of time in society to fix these problems that we make for ourselves. So that's kind of the thing. I am curious, did you guys like the lesson? Did you learn something new about this from this lesson? Because usually I kind of feel like most people know things about the clouds, so I was a little worried whether you guys.
I don't know my clouds. I'm an odd person. I'm an odd cloud. I don't know anything about clouds. I only like weather patterns, meteorology related things.
I tend to stay away from
Ignore
everything.
the Alexa. But I did learn a few new things, so thank you.
Yep. Any other questions, guys? Did you get something out of the lesson? Do you like the lesson, guys?
I did.
Yep. And yeah, tell us.
But I have a question. So global warming is happening because of the ozone layer being destroyed, right?
Partly. It's not the only reason, but it is part of it, yes.
Another question.
So basically, when you're talking about global warming, right, there are several different factors that play into it. One of them, of course, is chlorofluorocarbons, because they are destroying the ozone layer and allowing higher emission rates for UV rays. Another reason is the emission of methane and carbon dioxide, which act as greenhouse gases, and they're able to basically trap in a bunch of heat in our atmosphere, and which results in higher temperatures across the entire world. So there are multiple reasons that lead to the entire thing.
So what I'm saying is that if right now is the ozone layer being like less destroyed, because you said that before they didn't care about the CFC, but now when they care about it, isn't global warming starting to be more of a thing now and not before?
So here's the thing. I would say the ozone damage that we did a lot in the 80s and 90s, we've become a little wiser and are not doing it as much anymore. At least in developed countries. In developing countries, I still don't know. Maybe we're still causing a lot of damage. But it's a process that takes time. So I would say our effects of global warming are still accelerating today, not because of damaging the ozone, but us just increasing the amount of greenhouse gases into our environment. So stuff like methane and carbon dioxide, what's going to happen is that this CO2 and this methane, they're going to pile up in the stratosphere and mesosphere. And as they do that, what they basically do is make heat trapped. And if you trap heat, that increases the heat that we feel outside. So it makes the outside feel hotter, and that can cause a lot of effects to animals, the environment, increase our water usage. And it's also going to cause droughts because our natural pattern of creating rain is going to be interrupted and changed.
I have a quick question.
Yes?
I don't think I was listening when you were talking about this, but what's the Karman line?
I don't think we actually talked about it. Chivin, do you want to talk about it?
So the Karman line is basically, it's like a boundary where we're differentiating between space and our atmosphere. Even though there is technically an atmosphere beyond the Karman line, we usually don't worry too much about it because it's such a small amount. It doesn't have a lot of gas. It's a very light layer.
So
it's basically a line scientists draw saying, okay, beyond it is space, inside is actual atmosphere.
So let me best define to you the Karman line. So the Karman line is what scientists defined as 62 miles above the Earth's, above sea level. And when you reach the Karman line, it's usually a point where if you reach that point in the sky, scientists determine this point is too little, there's too little air for planes to generate lift and fly through. So planes, if they cross the Karman line, they can't keep flying higher and higher. because the air atmosphere becomes too thin for aircraft and planes and helicopters and all kinds of stuff to fly beyond that. And that's basically. Mm-hmm.
Airplanes can go farther than the troposphere. They can go to the stratosphere and the mesosphere.
Yeah, airplanes mostly chill inside the stratosphere. Very few airplanes really hit up the mesosphere. Usually very specialized fighter jets or stuff like spy planes or stealth aircraft. Those are the ones that usually chill up near the mesosphere, but most of them just hang around in the middle of the stratosphere. So yeah,
they can go to the Karman Line, or they can't go at all.
It's very difficult for most airplanes to hit the Karman Line. Proof.
And after that, they just can't go.
Some people talk about the thing called like the edge of space. So are they talking about the Karman Line?
Yeah, basically.
We have quizzes today.